Hello everybody and welcome to another, I guess this is my second kind of binary video in a row. I learned a little bit about this yesterday in doing research, and it's pretty interesting stuff. So today we're going to be learning about bitwise operators. So we'll start off with the bits, and then we'll look into the operators, and then we'll look at a couple of nifty tricks that you can do with these operators. So first thing, what is a bit? Well, a bit is the smallest unit of memory that computers have. They are the true zeros and ones. You hear, well, booleans are this and that, but booleans actually take up a byte, which is a total of 8 bits. And you can do a lot of things if you manipulate individual bits, because think about it, it gives you 8 times as much memory. There are a bunch of purposes for these, and encryption, specifically AES encryption, there's a lot of bit shifting. And storing flags, like for graphics, which we are doing in OpenGL, you can have 8 flags in 1 byte rather than 1 with a boolean. Like, think about it, if you had a boolean value to store, is this on or off, and say like bool on is equal to true, or you could store the values of 8 booleans using an unsigned char on set, and you could store the states of 8 different values, and this is very crucial for memory footprints. You can use a lot less, 8 times as less memory, to be exact, with bytes, if you manipulate individual bytes, or not bytes, bits rather. Alright, so we're now going to look at a couple of operations. So let's start with how you can represent bits. So in C++, you can do a couple of things. You can either do an unsigned char C, and you can assign it a number, like let's say this is equal to 16, and that's going to be equivalent to the bit 0b and then 10000, I believe, because that's 2 to the 5th. Is that right? Yeah. And you can also just say unsigned char C is equal to 0b10000, and that's what we're going to be using today. Alright, so we'll keep C like that for now, and let's look at our first operation, which is shifting. So when I talk about shifting, I literally mean you're going to be shifting bits. So there are going to be 2 different operators. You can go left or right. So let's take a look at the first one. So standard C out, let's say C left shift 2. So what this is going to do is it's going to take the 1 here. So let's actually just write this out in a comment. So let's just use 8 bits, because an unsigned char is 8 bits or a byte. So we're going to say 0, 0, 0, 1, and then 4 zeros, 1, 2, 3, 4. And we're going to shift it left by 2. This means that we're moving all the bits over by 2. So this is equal to 0, 1, 0, 0, 0, 0, 0, 0. And we should get a 64. So let's actually just run this just to make sure we do. And we get a 64, so that's good. And you might be saying, isn't that just 8 times 2 to the 2? Just keep that in mind, just an afterthought. Let's try right shifting now. So standard C out. When I'm using these in with the C out, that's just passing in bits essentially to a output stream. So it kind of is like shifting, except it's just transferring them. So let's do C right shift with 2. You might predict what we can get. Standard end line. We're going to get a 0, 0, 0, 1, 0, 0, 0, and we're right shifting by 2. This means that we're shifting all the bits over by 2. So we're going to get 5 zeros on the left. So 1, 2, 3, 4, 5, 1, 0, 0, which is equal to 4, which you might be thinking, this is actually 16. So might be thinking, that's 16 divided by 2 to the 2. Just interesting. All right, so that's shifting. One note about shifting is that there isn't out of bounds stuff. So if you run out of memory in a thing, it will just chop it off. So let's say that we set n or c is equal to 0b 1 0 0 0 1 0 0 1, like that. That's 137, I believe. So this is equal to 137. And let's go ahead and say standard cout, and let's go n left shift by 2. Let's see what we get. Oh, not n, sorry, c. We get a 548, which is 137, and then if you left shift the bits by 2, which is multiplied by 4, that's what you get, 548. And the reason why you do that, the reason why you go above the storage value for an unsigned char, which goes from 256 or negative 256 to 256, that's just 8 bits in either way. The reason why is because this just converts it to an integer. It just allocates the amount of memory that you need. Now, if you were to, so this just is automatically casted to an integer. Now, if you were to cast this to an unsigned char, that's different. So standard cout unsigned char c left shift by 2. Now I gotta freaking move all my comments over. Hold on. So this is now equal to, well, let's see what it is equal to. It should be less than 256, and it's a $sign. And the reason why we get a $sign is because that's just the numerical value, or that's the ASCII character. So we get print out a $sign, and the ASCII code for a $sign is actually 16. No, not 16, 36. And you can see that that's reflected in here by saying 1000101, the original, left shift by 2 is equal to 001000100, where you chop off the bits, which is equal to 36. So we're essentially chopping off the extra bits because we have a memory constraint when it's an unsigned chart. Yeah, so that's the out of bounds. Let's do, I'm going to introduce a topic now that we'll be using throughout this little tutorial or video, something called flags. So flags and states. I'm not talking about the 50 states of the US. I'm not talking about the flags of the UN building. I'm talking about states of individual objects in anything, really. You know, you could say on, off. That's pretty much what it is, on and off for 8 different states in a byte. So let's say, so we're going to have an unsigned char, AS, and we're just going to use this to store active states. I'm just abbreviating it. And this is equal to 0B11001111. So if you were to interpret this, this would mean that the first 4 states are active, and the last 2 are also active, but the 5th and the 6th states are inactive because they are at 0, which is switched off essentially. And then I'm also going to have 2 just placeholder variables. N1 is equal to 0B1000, which is 8, and unsigned char N2 is equal to 0B110010, just like that. So that is 8, or not 7, 8. This is equal to 26, and this is equal to 207. Alright, so let's look at our first bitwise operator, and it's going to be the bitwise AND. You typically name them with capital letters, and this is going to be the ampersand, so it's just a single one. And this just tests where bits are both active. And so let's go ahead and print out something here. So standard cout integer of unsigned, and we're going to cast an unsigned char to an integer. Here, no, let me just write it out. So why is that insert. So we want to go N1 and N2. So what this is doing is it's just doing a bitwise AND between N1 and N2. It's getting the unsigned char, so we're constraining the memory, and then we're just converting it to an integer, so we don't have to go to the ASCII table and get whatever. So it just makes it easier on us. Okay. All right, so we get a number 8, and let's look at what the number 8 looks like. All right, so let's say 8 decimal, and that is 1000. All right, so let's look at what AND is actually doing under the hood. So if we do 01000, which is the N1, and then AND it with 11010, which is the second one, and I'm just going to put the result down here. What you're going to get is we're just going to essentially take where both bits are 1. So first one, you have a 0 and a 1, so that's a 0. It's essentially like Boolean AND, where they both have to be active. So then we only have a 1 and a 1 there and there in the first, or in the second one from the left. So that's going to be the only one there. So it's going to be 01000, which is equal to 8, which is good. All right, so some applications of using the AND operator. You can go ahead and check a state using AND with 1 at that bit. So what do I mean by that? I'm going to say standard cout, and we're going to convert it to an integer again. You don't have to convert it to an unsigned char every time, just because in these we're not shifting much, so it's not going to go out of bounds, or it's not going to go out of 8 bits, rather. So the integer of AS, and now how do we want to do this? Let's consult our or not. Let's not consult anything. Let's just type this out real quick. So if we want to test, so let's get our active state. So we're just going to test the active states here. If we want to see whether or not, if we want to return nothing but the third state, so 0, 0, or there, how are we going to do that? So there's a trick that you can do with AND, God, I can't say this too many times. If you use AND with 1, you're just going to get the original string back. So essentially all we have to do is just AND it with a 1, but the 1 is only at that state. So we're going to be a 0, 0, 0, 0, 1, 0, 0, 0. And then if we AND the 2, you see that the bits only overlap right there, and we are just returned with that, which is an 8. So the way we're going to write that in code is AS, the active state, bitwise and then how are we going to get this? We're essentially going to take a 1 and shift and left shift it by 3 bits. So a 1 is equal to 0, 0, 0, 0, 0, 0, 0, 1. And then if we left shift that by 3, we're going to get a 0, 0, 0, 0, 1, 0, 0, 0. So we're essentially just shifting the 1 over by 3. So that is how you can check a state using AND. All right, next, bitwise operator. This is going to be the bitwise OR. So bitwise OR. This is by the single pipeline, or I don't know what that character is called. It's something. And this is going to see or test whether either of the bits are true. So let's look at this. So standard cout, we're going to convert to an integer N1 bitwise OR N2. So let's try and predict what this is going to produce. So we're going to have this. I'm just going to copy this over here like that, and we're going to OR the 2. So let's go through them. Oh no, that's the wrong one. I want to get this one because we're doing N1 and N2. So these two. Delete those. All right. So let's look at this. So only one of the bits has to be true. Both of them can be true, but only one. So essentially what we're going to do is we're going to look at the first one, 1, 0, that's true. 1, 1, that's also true. 0, 0, none of them are 1, so that's 0. 1, and then 0. And this is equal to 26, I believe. So let's go ahead and run this, see if we get a 26, and we do. Good. So that's Bitwise OR. Now, an example of how you can use a Bitwise OR is you can use this to actually activate a state. So activate state. So this is going to be switching it from either on to on or just off to on. So you can do either one because it's an OR. So the way we're going to do that is we're essentially going to take AS and we're going to bitwise OR it. So we're going to do bitwise OR equals, and then we're going to do the same thing that we did above, where if we want to activate the fifth state, we're just going to left shift 1 by 5 like that. And then we can standard cout int AS. And what we should get is I just have my reference over here, but let's just write this out. So AS is this, and we are bitwise ORing it with 1 shifted over by 5. So we have 1, 2, here, let me just, so 1, 2, 3, 4, 5, and then so shift it over like that. And if we bitwise OR the two, we're just going to do the same exact process. So we're going to get a 1, 1, 1, 0, 1, 1, 1, 1, just like that. And that I believe is equal to 239. And if we run this, we should get a 239, and we do. Good. Can I make this bigger? I can. Look at that. All right, so I'll just leave that open then, so you guys can see that. So that's how you can activate a state. And we have seen this in the past, in OpenGL specifically, because you can also use this to combine states and flags. So combining states and flags. So when we do like GL clear, when we call the GL clear GL color buffer bit, GL depth buffer bit, when we do this, this is essentially doing a bitwise OR, and these are 2 bits. It pretty much says it in its name. So per se, let's look at what this could look like. Let's say that GL color buffer bit is equal to 0, 1. It's just equal to 1, and then GL depth buffer bit is equal to 0, 0, 1, like that. If we were to OR the two, what we would get is just a 0, 0, 1, 0, 0, 0, 1. And that would equate to having both of those states active. So you can test to see if they're active using the bitwise AND, which is where that first operator comes into play. All right, next operator is a bitwise NOT. It's the complement operator. Not giving you complements, it is the complement as in the opposite. So it fits together perfectly. So bitwise NOT. So it's a complement. So it's going to flip all bits in a number. So let's just see. So if we standard cout the integer of the complement, the bitwise complement of n1, let's see what we're doing here. So if we take the complement of n1, which is 0, 1, 0, 0, 0, this is going to equal to, we're just going to flip everything. So we just see 1, 0, 1, 1, 1, which is equal to 23. And if we run this, we should get a nice 23. What happened? -9. That's not right. Oh, you know why? Because it's not yeah. Because it's treating it as 8 bits, but we actually only gave it 5. So let's say, let's get the complement of 0b 0, 1, 0, 0, 0, 0, 0, 0. And that should give us, let me just make sure that that's 8 actually. 1, 2, 3, 4, 5, 6, 7, 8, and that should just give us a 1, 0, 1, 1, 1, 1. I can't even count, I'm losing count. And what is this in decimal? That's 191. So don't know what it's not. You can use this to actually inactivate a state. So we can go ahead and inactivate a state. And the way you can do that is just say AND the bit with 0. So we're going to AND bit with 0, which will always result in 0. So always results in 0, but we have to keep or don't touch others. And the way you do that is, I talked about earlier, is if you AND it with 1, which returns the original. So AND 1 returns original. So what we want to do here is we want to say AS and bitwise AND equals, and then we're going to take the complement of something. Don't know yet, but it'll be something, and then we're going to standard cout integer AS. All right, so let's look at this on the keyboard. So if we take the current one, which is actually this updated one, because we did the Bitwise OR equals, so we actually updated the value, and we want to get the result that inactivates the fifth state, so it's going to give us the original. So the way we're going to do that is we're going to AND it with 1, everything but the bit that we want to inactivate. So 1 1 0 1 1 1 1 1, and then just AND it with that, and that's what we get. Now, how do we get this? We're essentially going to go ahead and take the complement of 1 left shifted by 5, which is equal to the complement of 0 0 1 0 0 0 0 0, which is equal to our number here, or byte here, which is that. I'm not going to run that just because it's not going to give us the right answer. So 1, just like that. All right, so maybe it'll work. 207. That is right. I don't know why the other one's not working. That is 207. So that is the Bitwise NOT. All right, last operator. The Bitwise exclusive OR. So Bitwise XOR, or the exclusive OR. This is symbolized with the caret, and this will return true if one is true, if one is active but not the other. So only one of them can be. So let's do this. So standard cout the integer of n1 bitwise XOR with n2. So let's look at how this will work. We're going to say 0 1 0 0 0 like that, and then we're XORing it with 1 1 0 1 0, and then like that. So only one of the bits is active. So the first one, that's true. The second one, both are active, so that returns false. And then the next one is both 0, so that's none. And then that is 1, and then a 0 at the end. And I believe this is equal to 18. So let's actually run this and see if it works. And we get an 18. Good. All right, so with the exclusive OR, we can do a couple of things. Well, the main thing that we can do is we can just use it to flip a single bit and change it regardless of its current state. So if it's active or inactive, we just want to flip it no matter what. And the way we're going to do that is, well, let's look at how we're going to do that. So we're going to do AS. Let's say that we want to flip the fifth bit. So XOR equals something. So let's, and then we'll print this out. So we have our original one, or the result from the last one, which is the original, and we're going to XOR it with something that returns the flipped bit. So we should get a 1 1 1 0 1 1 1 1 1. So what are we going to XOR it with to return that. Now, what you do is you essentially just XOR everything with a 0 but that one bit. So you get XOR with a 0, 0, 1, 0, 0, 0, 0, 0. And you're probably seeing patterns that you're going to do it with something with 1 shifted by the state. That's what we've been doing so far. And essentially how this works is if you XOR bit with 1, it just switches it no matter what, because if a 0 XOR 1 is 1, 1 XOR 1 is 0. So that's how that works. And then you just do the others with 0, which returns original. So I can actually just type this out real quick. So if you have a 0 and a 0, the result is a 0. 1, 0 returns a 1. 0, 1 returns a 1, and 1 and 1 returns a 0. So what we're going to do is we're just going to do the same thing. We're going to shift a 1 over by 5. So we're going to XOR it with 1 shifted to the left by 5. And I'm not sure what we should get. Let me run it and see if we... 239. That looks right, yeah. So this is equal to 239. Another cool thing that you can do with XOR is you can actually just flip it. If you do the same thing again, you're just flipping bits twice. So you're going to get the original, if that makes somewhat sense. So let's take this and we'll just say repeat again. So returns original. So let's see this. So if we do the same operation, so AS XOR equals with 1 left shifted by 5, what we're going to get is some operation that looks like this, which is the result from the last one, and then we're XORing it with the same exact thing. And essentially the operation is just going to do the reverse. So we're going to get a 1, 1, 0, 0, 1, 1, 1, and 1, just like that, which should equal 207. I'm not going to check it. No, we can just print it. Standard cout int as std and l. We got a 207, which is right. Okay. Yeah, so those are the 5 different yeah, that's right. The 5 different operators. Well, 6 if you count left and right shifters. So we have the left and right shifters, bitwise AND, bitwise OR, bitwise complement, and then bitwise exclusive OR. So we looked at that. Now we're going to look at precedence of this, and then after that we'll look at some tricks and cool things that you can impress your date with. Let's talk about precedence. So what comes first? What came first, the chicken or the egg? I don't know. But with bitwise operators, the first thing that will come is bitwise NOT. And this is paired with the plus plus, the minus minus, etc. Any operators that we'll call these unary operators that only that apply to that one thing. So they only have that one argument. So you just apply them immediately. Next, we're just going to put this in context with our arithmetic operators, just because you can combine the two. So multiplication, division, modulo, that comes second. The third is addition slash subtraction. Fourth is the bitwise AND. Fifth is the bitwise OR, and then bitwise exclusive OR, and then the sixth is the bitwise OR. So that's just precedence. So you could kind of play with this shit, see how it works. It's pretty fun. All right, now what you've all been waiting for, the 16 tricks. 16, I don't know, how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, 9 tricks to impress your date on the first date. Oh my god, just have them wet by the time they get in the cab. Jesus. All right, so here are a couple of tricks and optimizations. So first one is, I think we talked a little bit about this, is quick integer division and multiplication by powers of 2. So let's say that we had standard cout, and let's do 3 and left shift it by 2. What we should get, I'm just going to run this at the end, we should get a 3, we should get a 12, which is equal to 3 times 2 to the 2. Let's do standard cout, 15 right shifted by 2. This will give us a 15, this will equal 3, which is equal to a 15 floor division by 2 to the 2. I'm just putting the floor division there. That's what you do in Python, but I'll just write floor division because it's just integer division. A couple of other things that you can do with the AND, OR, and XOR. All right, the 3 main operators: the AND, OR, XOR. I'm not going to put any compound transition words between them because I can't speak English. All right, if you do A and 0, you get a 0. That's just how that works. If you do an A and 1, you get a 1, or you get the original. Because if A is 0, 0 and 1 is 0, and that's the original. 1 and 1 is 1, which is also the original. Now, if you do an A or 0, you get the original, because anything ORed with 0 just gives you what the A is. That was circular reasoning. A or 1 is equal to 1, because that will always return true. If you do A XOR 0, you get the original, because you don't flip anything. If you do A XOR 1, this is equal to the complement of A. And a cool little thing that you can do with the complements is, if you take the complement of 0, you just get the maximum integer. So it's equal to max int. I mean, think about it. If you have, let's see, so one integer is 32 bits, or yeah, 4 bytes, 32 bits. So that's equal to 0, integer 0. If we took the complement of that, we're going to get all of this, but just replace it once, like that, and that's just equal to int max. That really gets them all the time. Just amazing. Like, you don't even got to include limits.h. You can just say, oh, give me the bitwise complement of 0. All right. Now for a little bit of odd and even determination. If you do a and bitwise AND it with 1, if that equals 1, it's odd. I'll just write this as a ternary, just because I'm really cool. So if that returns true, it's odd, else even. Look at how cool I am. That's just because if the last bit is 1, it's going to be odd. And if you AND it with a 1, you're going to get a 1. And AND it with a 1 means zeros for the rest of the bits, so those are all going to cancel to 0. All right. Next is, we talked a little bit about the cycling of exclusive ORs. So if you do A XOR B, XOR B, XOR B? What? Isn't that a toy? The two XOR Bs cancel and you get A. So flip twice, XOR B, cancel. Now another cool thing about this is that XOR is commutative. So this means that A XOR B is equal to B XOR A. Now this is pretty much true for all of these, except for the shifters. And this can actually help us do something cool, which is swapping integers without a temporary variable. So we can go ahead and flip integers without a temporary variable. So let's say that we have int A is equal to 96 or 90. I typed in 92 and I said 96. All right, whatever. So pointer to A is 92 and pointer to B, or we can just say A is equal to 92, B is equal to 36, just like that. So the way to swap them is, let's first do an XOR A of B. So A XOR equals B. And then next we're going to say B is equal to A XOR B once again. Now what does this give us? So let's look at this. So this is equal to the original A, so A underscore 0, XOR B underscore 0, which is the original. But this, so that's just this operation here. This is just, this is equal to A original XOR B original. And then I'm just taking A that, which is equal to A original XOR B original XOR B original, which is equal to A original, because the two B's cancel out. These two cancel out right there. Now to go the other way, if we want to get B to the A to the B, B to the A, we're going to say A is equal to A XOR B. Once again, we have actually just performed the same operation 3 times. Now, what does this do? Well, let's look at this. So this is equal to A XOR B. Well, that's what we have there. Now, let's substitute in A. So A is A original XOR B original, and all of that XOR the A original, which is just the current B. Now, using the commutative property, we're going to say that this is equal to B original XOR A original XOR A original, and those two A originals cancel out, and you get a B original. That's just by the commutative property. So yeah, that's some pretty cool stuff. Yeah, and that's whatever, bitwise operators in general. Little half chub of a video to come out. I mean, I wouldn't really consider this a programming challenge, but you know, it's some pretty cool stuff, and we will be learning this or using this in OpenGL in the next couple of days, hopefully Tuesday, I don't know. But yeah, that's all I have for you guys today. That was bitwise operators.